Greetings and welcome to part 2 of the How Volcanoes Work PowerPoint. So we're going to continue with the presentation, and we're going to start by focusing on the smallest of the three volcano types. These are scoria, also known as cinder cones. And the thing to appreciate about cinder cones is not only that they're small compared to both stratovolcanoes and shield volcanoes, but especially that they're not really made of lava primarily. They're made out of pyroclastic fragments about the size of walnuts or peas. So pea to walnut sized pyroclastic fragments that we informally call cinders. And essentially what a cinder cone volcano is just a pile up of material right around the vent. So the idea is that when the volcano erupts, it's erupting a little bit explosively, but not very explosively compared to a stratovolcano. And the cinders are large enough that almost as soon as they erupt, they fall back down and collect around the vent to build up this sort of loose pile of cinders that becomes the cinder cone volcano. And in this slide, there are just a few examples of actual cinder cone volcanoes. That's Sunset Crater in the lower left-hand corner. That's a prominent cinder cone just outside of Flagstaff, Arizona. And then in the upper middle, that's actually a smaller volcano, a smaller cinder cone volcano on the flank of a much larger shield volcano known as Mauna Kea. And then there's the Pu'u'o'o cinder cone in the middle bottom portion of the PowerPoint slide. We talked about that in the previous presentation. Right now, the Pu'u'o'o vent on the Big Island of Hawaii is where active volcanic activity has been ongoing for the last few decades. And then finally, in the upper right corner, there's an example of another cinder cone in Arizona. And that black stuff kind of emanating from the bottom of the cinder cone is actually a lava flow. But the volcano itself, in all of these cases, is made out of fairly loose material that we call cinders. That's what cinders look like up close. They're technically called lapilli. You don't really have to remember that, but what you do want to remember is that each of those little fragments is a pyroclast, meaning it was explosively ejected from the cinder cone volcano before it landed on the ground. A good example of how an actual cinder cone volcano erupts. So it's certainly explosive, but as we'll see, it's not really that explosive in comparison with a larger stratovolcano eruption. Well, what comes out of cinder cones when they erupt? Certainly gases. That's going to be true for all volcanoes. Primarily water vapor, but also other gases as well. Sulfur dioxide, carbon dioxide, carbon monoxide, even gaseous hydrochloric acid. And in this case, in kind of the lower left-hand portion of the diagram, we're looking at a really interesting large pyroclast. Almost looks like a football. That's known as a volcanic bomb. And what happens, it's sort of like a giant lava droplet that gets ejected from the volcano, and it gets blown up into the air, and it actually cools in the air. And then on its way down, as it's still cooling, it kind of assumes a sort of football aerodynamic shape. And then by the time it lands on the ground, it's already solidified. That's how quickly these volcanic bombs cool. And we also get lava flows, sometimes associated with cinder cone eruptions, as well as spatter. Spatter is just liquid material that gets blown out of the volcano that's still liquid by the time it falls back down to Earth. Okay, now we move on to the quintessential subduction-related volcano, what's called a stratovolcano, also known as a composite cone. And the key idea here with this type of volcano is that it's composed of layers or strata. And the layers alternate between being lava and also pyroclastic material. So you can see in the upper left-hand diagram, the lava layers are darker colored inside the volcano, and then the lighter colored layers represent explosively ejected material that either flows down the flank of the volcano or falls back down to Earth once it's been blown up into the air. And so the key thing here is that we see alternating layers of cooled, crystallized lava, but also layers of generally loose pyroclastic material as well. That's why we call it a stratovolcano, because of the strata, because of the layers. The other really important thing you want to remember about stratovolcanoes is that they're a result of highly, violently explosive magma. And then the third thing that's very important about stratovolcanoes is that this is mostly the type of volcano we see at or very near subduction zones. Mount St. Helens in Washington is a good example of a stratovolcano. And by the way, this is a picture of the volcano before the 1980 Mount St. Helens eruption. After the eruption was over, several hundred feet of the top of the volcano was obliterated during the eruption. Often, stratovolcanoes have relatively steep sides. You can especially see that with Mount Mayon in the Philippines. And again, what you tend to see mostly during stratovolcano eruptions, because they're so violent and explosive, you do get some lava, but mostly you get pyroclastic material. This is explosive material that gets blown up into the air, or perhaps rushes down the sides of the volcano. And when you look at this material up close, you can see that it consists of different fragments. So what I'm circling right here is not a single crystal. That's actually a fragment of explosively ejected material. And then particularly if the fragments are still relatively warm or even hot, once they hit the ground, they can fuse together, or even long after they land on the ground, even if it's just a loose layer of fragments at first, if you get later mineral-rich groundwater that kind of percolates through the material, or Mother Nature can kind of fuse it together in that case. So again, how does a stratovolcano erupt? Very explosively, very violently. And what tends to happen at first is very often the eruption is somewhat vertical, and you get an eruption cloud that builds up above the volcano. And then when the eruption cloud reaches the upper atmosphere, atmospheric winds can kind of spread it out, and then eventually the fragments can fall back down to Earth, blanketing the landscape almost like a snowfall. That's called a pyroclastic fall. But the more dangerous sort of eruptive mechanism is when the pyroclastic material flows out of the vent and then rushes very rapidly as a hot mixture of pyroclastic material and gases kind of down the flanks of the volcano. That's known as a pyroclastic flow. You can also get volcanically produced mass movements, landslides, and also too, if the top of the volcano is covered with ice and snow before the eruption, very often a lot of that ice and snow will catastrophically melt during the eruption. It'll mix with the pumice and the volcanic ash and that material to create this sort of warm, soupy mixture of pyroclastic material and mud and water known as a lahar. You don't have to know that terminology, but a volcanic mud flow is known as a lahar. And lahars can be dangerous because they can move many miles, many miles outward from the slopes of the volcano. And then, as also shown in this diagram, as the magma kind of moves up from below into the throat of the volcano, the force of the magma squeezing into cracks actually can widen those cracks and even produce new cracks, giving rise to earthquakes. And so very often it's actually possible to get a sense of an impending eruption if you all of a sudden start seeing this sort of vertically rising sequence of earthquakes that are maybe a little bit deep at first, and then on timescales of days to weeks to even hours, you get increasingly shallow earthquakes. That tends to mean that magma is on the rise if the earthquakes are associated with the volcano. And in the non-animated version of this PowerPoint, I encourage you to click this link right here, and you can actually watch a short video clip that shows an absolutely spectacular eruption of a typical stratovolcano, in this case Mount Semeru in Indonesia. And you'll see what I mean when you actually see the YouTube footage, that volcanoes like Mount Semeru, they don't primarily erupt lava, they erupt pyroclastic material and gas, and they tend to do so very violently. Okay, well, I wanted to take just a few minutes to talk more about what happened in the historical eruption of Mount Vesuvius in Italy in the year 79. And Mount Vesuvius in this left-hand slide is actually an active stratovolcano. And when it erupted in the year 79, it completely destroyed the cities of Herculaneum and Pompeii. But as we'll see, the destruction occurred in different ways and for different reasons. What happened in Herculaneum is, after the initial eruption began and then started to wane, it started to lessen. The eruption column that had already developed above the volcano could no longer be supported because less new material was coming out of the vent, and that caused the eruption column that had already built up over the volcano to collapse. And at that point, a pyroclastic flow developed that roared down the slopes of Mount Vesuvius and completely covered up the town of Herculaneum. In contrast to that, the town of Pompeii was also buried, but it was buried by more of a pyroclastic fall as opposed to a pyroclastic flow. And in and around Herculaneum, that pyroclastic flow in some places was up to 20 meters thick, if you can imagine. Whereas at Pompeii, the pyroclastic falls that buried the city weren't quite as thick. So just a couple of artist renditions of what that volcano might have looked like in places like Pompeii and Herculaneum when the eruption was happening. This is Mount Vesuvius today. You can see it's covered with ice and snow, and so we might very well expect during the next large eruption of Mount Vesuvius that ice and snow would mix with the pyroclastic material and the hot ash and the gases, etc., to create these sort of soupy flow deposits called lahars that could roar down the slopes of the volcano. And very interestingly, when way back in, I want to say the late 1800s, when archaeological excavations at Pompeii first began, archaeologists noticed cavities in the ash and the pyroclastic material as they were digging through it to uncover the city. And in many cases, they noticed skeletons of both people and animal inside these strange-looking cavities. it was eventually realized that the cavities themselves had the shapes of both people and animals. And so what some of these early archaeologists did is, once they opened up the cavity and once they realized what it was, they filled some of the cavities, you can see in this upper left-hand slide, with plaster of Paris to, in effect, recreate the shapes of the bodies that were entombed in the ash during the eruption. So this is what Mount Vesuvius looks like today. And you can see how incredibly populated the area is around Mount Vesuvius. And so essentially what I'm implying here is that Mount Vesuvius is a ticking time bomb. There's no question that it will erupt again in the future. And if it produces a large eruption, the millions of people who live near the volcano could certainly be at risk from hazards like pyroclastic flows, pyroclastic falls, perhaps lava flows, and also lahars, volcanic mud flows. So I want to finish this second presentation with a quick discussion of the so-called active volcanoes east of Mesa College. And the area that I'm speaking about is about 3 hours by car to the east of San Diego on the southern shore of the Salton Sea. And in this area, this is the region that sort of connects the southern end of the San Andreas Fault to the north with the northern end of a different plate boundary fault called the Imperial Fault to the south. And what's happening in this area in between the San Andreas Fault and the Imperial Fault is, you can kind of see from these black arrows right here and right here, is that this area is actually being stretched in tension. And because of that tensional stretching, that actually melts rock at depth, and it provides cracks up through which the magma can move. And in the case of these Salton Sea volcanoes, the magma has recently migrated all the way up to the surface to produce a series of 4 different volcanoes there on the southern shore of the Salton Sea. So, and specifically what's happening in these areas is we have regions of plate divergence. And so, although we have a transform boundary both here to the north along the San Andreas Fault and also to the south along the Imperial Fault in this area, the area in between the San Andreas and the Imperial Fault is actually a buried spreading center. We think that there are several buried divergent boundaries out here in the Imperial Valley south of the Salton Sea. And because the lithosphere is being extended, it's being pulled apart in tension in those areas, just like you would along a mid-ocean ridge, you get volcanic eruptions. Except that in this case, the actual mid-ocean ridges are buried by mostly Colorado River sediments that have flushed into this area over the last few million years. But this is an area of active volcanism, especially on the southern shore of the Salton Sea, and then also in all of the white areas that I've circled. We get particularly high heat flow. And in fact, this entire area, kind of throughout the Imperial Valley and also south of the border in northern Mexico, this is an area of high heat flow. And all of the red dots in this area represent geothermal power plants, where power companies have learned to harvest the heat associated with the rising magma in this area and turn it into steam to power turbines to generate electricity. So here's a quick Google Earth image that I've annotated, kind of showing the locations of these different volcanoes. They're known locally as the Salton Buttes, and they include from south to north Obsidian Butte, Rock Hill, Red Island, and Mullet Island. And what do we see in these areas? Well, these are just some examples of what the volcanoes actually look like today. There's my Jeep for scale. This is Red Island, the southern part of Red Island. This is Rock Hill, right there, almost on the shore of the Salton Sea. And then in the background here, that little blip is Obsidian Butte. And then what we're actually seeing here, these little white plumes that you can see inside the yellow circle, are actually steam plumes from geothermal power plants to the south. Okay, well, let's do a quick recap of the really important ideas when it comes to volcanoes. Can you answer this? In what settings do volcanoes typically erupt? Certainly at subduction zones, as we've talked about, also divergent boundaries, as well as atop mantle plumes. And I would add to this a fourth setting, which includes areas of crustal extension, what we sometimes call continental rift zones. When one continent breaks up into two, or perhaps even when a supercontinent like Pangaea breaks up into many smaller pieces, when the breakup first starts to occur, we don't yet have a divergent plate boundary, but we do have the very beginnings of plate divergence. That's what a continental rift zone is. And a good example of active volcanism in a modern day continental rift zone would be Mount Kilimanjaro in East Africa. Can you name the three most common types of volcanoes? Well, I bet you can. We covered that earlier in the presentation today. They include shield volcanoes, which are the largest type of volcano and have very gentle side slopes. Also stratovolcanoes, which are highly explosive and the most violent. They tend to have steep sides. And then finally, steep-sided cinder cones, also known as scoria cones. These are the smallest type of volcano. What are the main eruptive style controls? In other words, what factors play an important role in influencing how a volcano will erupt? That's what I mean by eruptive style controls. And there are three of them, three principal controls, including gas content, silica content, and temperature. And the way this works is gas content is maybe the most obvious. If you have a gas-charged magma, that's obviously going to erupt more violently than a gas-poor magma. Remember, I said earlier in the first presentation of this two-part presentation that silica content is to magma as cornstarch or flour is to sauce. The more silica enriched the magma, the thicker the magma, that is, the higher the viscosity. And under those high viscosity conditions, the gases in the magma have trouble escaping. And if gases are preventing from escaping, even as gas bubbles are forming, that means that gas pressure keeps going up and up and up until the whole system explodes in a violent eruption, generating a lot of pyroclastic material. And then how does temperature play a role in how volcanoes will erupt? Well, here too, temperature can control viscosity. So another cooking analogy is if I put pancake syrup in the refrigerator, even as the temperature goes down, the viscosity, that is the thickness of the pancake syrup, will go up. Likewise, if I warm that pancake syrup on a stove, even as the temperature of the pancake syrup increases, the viscosity, that is the thickness of the pancake syrup, will decrease. And that produces a thinner, runnier magma, and that type of magma more easily allows gases to escape, preventing gas pressures from building up and ultimately leading to eruptions that are less violent, less explosive. Two types of basaltic lava include that one type that's smooth and ropey and that other type that's really rough and jagged. You might remember those two types of lavas as being pahoehoe if it's smooth and ropey, or aa if it's rough and jagged. And then it's not listed here, but remember that underwater eruptions produce, it's kind of like an underwater version of pahoehoe. It's called pillow lava. Explosive eruptions are characterized by pyroclastic flows. and also pyroclastic falls, as we saw in the case of Herculaneum and Pompeii during the eruption of Mount Vesuvius in the year 79. And then finally, Salton Trough volcanism out south of the Salton Sea occurs in an extensional step-over, kind of a transition zone between the San Andreas and the Imperial Faults. And this area is interpreted to be a subsurface spreading center that is a divergent plate boundary. And so like all divergent plate boundaries, we tend to get associated volcanism in this area. Okay, well, that pretty much does it. Thanks for listening. And by all means, get in touch with me if any of the material doesn't make sense. Thanks a lot.